13.4, dealing with tree diagrams. Just to give you an idea of what this is about, if you read this, it says, in this chapter we have introduced graphs as a means to represent problems from everyday life. We use graph theory to solve a variety of problems by finding Euler paths and Euler circuits. Remember, Euler paths and Euler circuits deal with the edges, not repeating any edges. It says we also use graph theory to find the optimal and approximate solutions to a traveling salesman's problem using Hamilton circuits. Remember, Hamilton circuits deal with vertices, not edges. It says we now turn our attention to another type of graph called a tree diagram, which is also frequently used to represent problems from everyday life. Okay, before we define a tree, let's look at example 1, in which we create a tree showing the supervisory relationship at a service company. All right, so here's example 1. It says construct a graph to represent the supervisory relationships at Handy Henry's repair service. Henrietta is the president, and she has 3 shift supervisors, Tommy, Patrick, and Susan. Tommy supervises 2 service specialists, Michael and William. Patrick supervises 2 service specialists, Amy and Noel. Susan supervises 1 service specialist, Rodney. So basically what they did was they did a tree diagram. So here's Henrietta, who is the president. Here are her shift supervisors, and here's the workers underneath them. Thus, the look of a tree. That's the reason it's called a tree diagram. A couple of things you need to make sure you understand. It says recall from section 13.1 that a bridge is an edge that, if removed from a connected graph, remember, connected graph is where all the vertices are connected, would create a disconnected graph. Thus, if you remove any edge in a tree, it creates a disconnected graph. Since each edge would create a disconnected graph if removed, a tree cannot have any Euler circuits or Hamilton circuits. Okay? So trees, the Euler circuit and the Hamilton circuit rules and theorems that we learned go out the window. And here's some examples of some trees. Another definition that we have here, and this is on page 837, says in this section, to solve certain problems, we will need to remove edges from a graph that is not a tree to form a tree known as a spanning tree. So a spanning tree is when we're looking at a graph and we remove edges. By removing the edges, it becomes a disconnected graph, which makes it a spanning tree. Here's an example problem of a spanning tree. It says Kutztown University is considered adding awnings above its sidewalks to help shelter students from the snow and rain while they walk between some of the buildings on campus. A diagram of the buildings and connecting sidewalks where the awnings are to be added is given in figure 13.48. So here we go. Here's the diagram. Here's the connection. So here's our vertices, which are the buildings. Here are our edges, which are right here. Okay? All right, so what happens here is this. It says, originally, the president of the university wished to have awnings placed over all the sidewalks shown in figure 13.48. But that was found to be too costly. Instead, the president has proposed to place just enough awning over a selected number of sidewalks so that by moving from building to building, students would still be able to reach any location shown without being exposed to the elements. Letter A. Represent all the buildings and sidewalks shown with a graph. B. Create 3 different spanning trees from this graph that would satisfy the president's proposal. All right, so first of all, it's pretty easy. The graph, we just make all these buildings vertices and just connect them in terms of the sidewalks. Then what happens is, first thing is we could drop all the outside sides. So do you see how, this outside side, this outside side, this outside side, this one, this one, this one were dropped to give that tree diagram? That would still allow them to be able to go from building to building to building. Then if you look at this tree diagram here, basically what they did was drop this and this, this and this, and then this. So we get this kind of a diagram there. And then in the last one, basically what we did was we dropped this side, then we dropped this side, and this one here. And we could still get there. So all three spanning trees would work. You'd still be able to get from building to building without getting wet. So here's another example problem. It says finding a minimum cost spanning tree. It says examine the weighted graph in figure 13.51, which is right here. It says the graph shows the cost in dollars associated with each edge. Determine the minimum cost spanning tree for this graph. All right. So if you see the tree we have, first we take away this side. We had 17 and 48, we get 65. Then we take the other side away. At 23 and 17, we get 50. Then we take the bottom away, and we get 71. So we can see that this one right here, letter B, is the cheapest. Now we come to Kruskal's algorithm. It says to construct a minimum cost spanning tree from a weighted graph, select the lowest cost edge on the graph, select the next lowest cost edge that does not form a circuit with the first edge, select the next lowest cost edge that does not form a circuit with previously selected edges, and continue on. So here's an example here. Here we have a weighted graph, and all the edges are weighted. And so if you look at this, it looks like the first edge we're going to select is going to be this 11. And because we select this 11, we now got to look for the next cheapest. Looks to be this 23, so that's the reason we go to 23. And then we got to select the next cheapest, which looks to be 31. So here we are. So then what happens is we want to go to the next cheapest. And out of the ones we have, see, we can't go from C to A, which really is the cheapest, 38, because it would be connecting these two and would be making it a connected graph. We don't want a connected graph in a tree. So what we have to do is go here to go to G to H, which is the next cheapest. And then we're going to go to the next one, which is H to F, which is 48. From there, you can see that now we're going to go for the 53 here, which goes from here to here. Then we're going to go to 57, which is right there. And we have our tree. We've included all the vertices. See, all the vertices are connected. And we have our tree diagram. And that's using Kruskal's algorithm, going from the cheapest to the cheapest and just making sure you don't enclose it to make it a connected graph. Last example problem I have here is on page 841. It says the Colorado Parks and Recreation Association wishes to build a bicycle trails that connect the cities of Aurora, Boulder, Denver, Inglewood, and Golden. The approximate distances in miles between these cities are given in the table. So here's the distances given in the table. If we come over here, we use and we just plot those cities. Here's the 5 vertices. And if we just start to go and we take the cheapest using Kruskal's, the cheapest or the smallest distance was A to D, which is 9, and then D to E, which is 8. Then what we did was D to G, which is 16. And then now what we're doing is we're going to go from 16 to B, which is 26. And so that's just doing Kruskal's algorithm here, where you take the lowest edge, start with the lowest edge, then you go to the next lowest edge. You just make sure you're not having any graphs connected.